Hi, welcome to Cambridge Technical Revision Unit 3, Direct Forces. By direct forces, what we're talking about here is compression and tension. Now we're going to look how we can calculate two particular values for these, or the impact of these on a material, which are stress and strain. And this will lead on to the Young's modulus for elasticity. When a material or an object comes under load, it can happen in one of two ways. It can be compressed or squashed, if you will. And when it gets squashed, or it comes under compression, it tends to change its shape, it bows out. It can also come under tension, the opposite. And you can see here the material pinches in as it's stretched out. You can see that as you stretch a material, you see it pinches in, but it changes its length. That change of length is going to become significant when we start talking about strain. The stress of the material, or how the material is being stressed, acts and is measured as part of its cross-sectional area. So we talk about stress being the force that's shared over the area involved, where the force is in newtons and the area is in meters. Force being mass times acceleration. The mass is in kilograms and the acceleration due to gravity 9.81 meters per second. So I'm going to take a notional object. Let's imagine an apple sitting on a cylinder. And for our purposes, the cylinder's got a diameter of 50 millimeters. And we'll say it's got a height of 50 millimeters as well. So let's say it's a large apple, perhaps a couple of 100 grams. The first thing we need to calculate then is the force that 200 grams would act downwards under an acceleration due to gravity. This is in grams though, and we want it in kilograms. So it should be 0.2 kilograms times 9.81 meters per second. It gives a force in newtons of, just so you can see it, 0.2 times 9.81 equals 1.962 newtons. Now that 1.962 newtons is acting over that cross-sectional area. Now if we want to compare that to other cross-sectional areas, then we need to sort of amalgamate that into a specific unit. And what we'll do is we'll do it for 1 meter squared. And we can do that by calculating the area and dividing it into the force. So we'll use pi r squared. We've got 50 millimeters. We'll need to convert that. So pi multiplied by, I like to use brackets just to keep things neat. Half of 50 is 25. 10 to the minus 3 gives us meters. And then I'm going to square that. If I work that out, 3.142 times bracket 25, that's times 10 to function button there, times 10 to the minus 3, close the bracket and square that, equals, very similar figure to what we got before, 1.96375, so I'm going to go 964, and that is times 10 to the minus 3 from there. Force divided by area. So the stress, this is the symbol for stress, is 1.962 divided by 1.964 times 10 to the minus 3. So we've got a force of 998.982 newtons per meter squared, and that is the stress. Now, while the object or the shape is experiencing stress, it's also changing its length. It's becoming either shorter or longer. And it's this change in length that allows us to calculate a value for the strain that the material is experiencing. And the strain is the change in length, delta meaning change, over the original length. So here we have a change in length, and here we have an original length. Let's imagine that this is a particularly soft material, say a sponge-like material, and we're placing the apple on the top, and let's say that the change in length is 5 millimeters. Then to calculate the strain, we would have change in length, 5 millimeters, divided by the original length, 50 millimeters. The value for the strain is 0.1. Now sometimes it helps to be able to discuss strain, and sometimes it's common practice to use a percentage. So you might say that the change in length of the material, it changes length by 10% of its original length. Now, there's no plus or minus for strain, it is just a value. Sometimes it's shorter, and sometimes it would be a longer value. Having a stress over a metre squared area means that you can compare different material stresses. Having a calculation for strain means that you can compare the material strain. And it was Young's that figured out that if you combine these, stress and strain, you could have a comparison for a wide range of materials. And this is the Young's modulus for elasticity, which is Young's stress divided by strain, because the symbol for strain, epsilon, is like so. And it's this that we'll be discussing in more detail in the next video.